Another topic that I hope you're familiar with is the oxidation states. Right now we just finished or working through, actually finished the redox one, so you should be a lot happier on oxidation numbers than maybe you were before. If we look at our periodic table there, make it pretty colours in terms of the groups so that we can then pull out another set of boxes in which I'm going to use the same colour scheme to put in the oxidation numbers. Hydrogen +1, -1, +1 of course when it's with less electropositive, more electronegative atoms, -1 when it's with the metals and so on. We'll have a completely separate movie or two movies associated with the hydrogen compounds of the elements. The rest of the group 1, all the alkali metals, trust you know they're +1. You see sodium in a compound is +1. Potassium in a compound is +1. There are some instances of so-called alkalides that we will touch upon, probably in your second year classes, in which Na-, for example, has been made. But they're so rare and they're so exceptional that any time we're going to say you see an alkali metal, it's +1 oxidation state. Same thing, of course, for the alkaline earths. They're +2. Right? Every single time they want to lose 2 electrons to become like a noble gas. Most of the time, you'd say for the icosagens, they're going to be +3. But I trust you remember from your GCSEs and A-level, the so-called inert S. And the idea of that is that when you move into these main group metals that have got S and P electrons, the smaller members of the group want to get rid of all of those electrons. The larger members, on the other hand, aren't too disappointed if they keep their S electrons and just lose the P's. So therefore you find for gallium, and then to a greater extent indium, and to a great extent for thallium, not just the +3 that you would expect when they lose the 2s and the p electrons, but the +1 that comes if they just lose the p electron. We see that same phenomenon for the lower members of the crystallogens. Germanium, mostly +4, but some +2. Tin, +2 and +4, very common indeed. Lead, you see +4, but more often than not is +2. And again, just let me remind you, you've got an S2, P2 electron configuration. The +4 comes when they lose all 4 of those electrons. The +2 comes when they just lose the p electrons, but keep the inert, in quotes, S pair. And the same idea for the last 2 members of the pnictogens, antimony and bismuth, +3 and +5 oxidation states available to them. Flipping to the other end of the periodic table, I'm going to have to cough in a minute, excuse me. We expect the halogens to be -1. The idea being, of course, that they're 1 electron away from being a noble gas, so they want that 1 electron, so they have an oxidation state of -1. Same way we'd expect the non-metal members of the chalcogens to be -2, non-metal members of the pnictogens to be -3, and carbon ultimately we would expect to be 4. But it's not as simple as that. If we look at chlorine, for example, yes, we can find compounds, very common compounds containing chloride in which is -1, but we can also find compounds in which it's +1, +3, +4, +5, +6 and +7. These kind of being compounds where the chlorine's got the positive oxidation state because it's with more electronegative atoms, either oxygen or fluorine. Thus, for example, +7 occurs in the perchlorates containing the ClO4- anion, +5 in the chlorates, the ClO3-, +3 in the chlorites, the ClO2-, and +1 in the hypochlorites, the ClO-, and then the oxide ClO2, ClO3, account for these even number oxidation states. In a similar fashion, of course, bromine and iodine can also form the hyperbromates, hyperiodides, the perbromates, and the periodides, and so on. Okay. Oxygen, just about all the time -2, but you can find it as -1 in peroxides, -0.5 in superoxides, and +1 and +2 associated with fluorine. And we'll talk a little bit about that later on. Sulfur, you can have -2, of course, but +1, +2, +4, and +6. Selenium, not very often in the +1 or the +2, but -2 and then +4, +6 again. These usually when forming compounds with either oxygens or the more electronegative halides. Tellurium, not often as the telluride is -1. There are some, sodium telluride, potassium telluride, but more often you find tellurium, which is of course a metalloid or a semi-metal, is going to have positive oxidation states. And polonium, the little bit of chemistry that's been done on polonium, usually polonium +4, not +6, because again, there's that inert S, right? It's a 6s2, 6p4, prefers to just lose the 4p electrons, keeping that inert S pair around. Nitrogen, you expect it to be -3, but extensive chemistry of the nitrogen oxides, in which it's +1, +2, +3, +4, and +5. Okay, so +1, where it's N2O, laughing gas, NO, NO2 minus, for example, the nitrite anion, NO2, where it's +4, and then nitrates, excuse me, NO3 minus, where it has the +5 oxidation state. Same kind of idea, but not nearly as varied for phosphorus. Phosphorus can be -3 as the P3 minus anion, but in nature particularly, it's +5 as phosphate, PO4, 3 minus, and then of course +3 with phosphites. Again, these positive oxidation states come when it's forming compounds with the more electronegative oxygen and the halogens. And then arsenic, very much behaving like phosphorus. It can have some -3 when it's with very electropositive atoms, but it prefers to be +3 and +5. Now, the last little bit that we haven't talked about, the group 4, particularly carbon and silicon. Carbon, of course, you think of it as being 4, it can be -4, it can be +4 depending on it, and it can also be +2. As you count oxidation numbers, you can also find organic compounds in which it's -3, -2, -1, 0, 1, and 3, as well as the even numbers here. We're not going to dwell too much on that. We'll leave all that for the organic chemist type things. Now, conversely, silicon you rarely find in anything other than its +4 oxidation state. There are a couple of examples, but +4 really is the dominant oxidation state associated with silicon. Now, much of the really interesting part of these oxidation states is associated with the chemistry of oxygen, right? I mean, oxygen itself is pretty interesting, right? -1/2, for example, is an oxidation number. That's kind of freaky, isn't it? But it's oxygen that gives, more than anything else, gives the range of oxidation number for the halogens and for the remaining chalcogens and so forth, and certainly for the nitrogen here, right? It's only oxygen and fluorine that can make nitrogen have positive oxidation states. And so the start of the next introductory movie, and also the theme of a couple of more detailed movies, will be the oxides of the various atoms. But anyway, been going for 20 minutes in this one. Thus it is time to stop it, turn it into a movie, and get myself another drink.